a puzzle on 8 blocks movement. So here is the respective puzzle description. A player is supposed to slide tiles into new positions in order to realign a scrambled puzzle back into a goal alignment. So this is our goal alignment here. So we are supposed to arrange these 8 tiles in such a way that we require to have this goal arrangement where the center point will be known as the empty spot or ES. So it will be known as empty spot or ES. We shall have to develop one procedure DFS which finds required moves to reach to the goal node without any repetition. And this DFS will have 3 arguments. So here we are having the first argument and the second argument, and this is the variable that is a path. So in this way, this DFS, this very procedure will get executed. I think for the better understanding, let us go for one demonstration where we shall discuss regarding this problem. We shall run it and outputs will be obtained accordingly. So demonstration is for you. In this Prolog program, we have implemented the 15 puzzle problem and its respective solution. So we know that here we will be having 15 blocks and one empty spot. So our goal arrangement of our board will be something like this. We are expecting that the empty spot will be at the middle and then other blocks will have the positions like this. Now what are the feasible possible movements are there? If the empty spot is in the top row, then either it can be at the middle place or it can be at this particular place. Because at the first place the empty spot cannot be, because in that case the left movement is not possible. So that's why we are going for a board position this, that is a source board position, and this is our goal or target board position. So in this way we are going for movement of the empty spot left in the top row. In this way we have done it. So we have considered 2 cases when the empty spot will be at the middle of the top row or at the right of the top row. So move empty spot left in the middle row. In the case, the empty spot can be at the middle of the middle row or at the right of the middle row, and in this way the board positions can have the can have the next board position, target board position, when the empty spot will move towards the left in the middle row. So that's why left in the bottom row, right movement in the top row, right movement in the middle row, right movement in the bottom row. In this way we have considered all the possible moves of the empty spot. So here you can find that all the possible moves we have done the respective lists accordingly. Now let me go for the solution. So at first we are going for DFS simplest. So in this case what is happening, you see, this is our source board position or the source list, and it will be the target list. The same list will be the target if the list is matching with the goal list. Otherwise S will be found as a head, and rest, how to form this rest, that is a tail part of this list, that is move S to S2 and DFS S2 from there will be forming this rest. So DFS simplest has been called here recursively. So in this way DFS simplest is working. That means it will just make the current board position as a first argument and all the board position intermediate while going to get our goal board position in the second list. Okay. Now let me execute one query on this DFS simplest. So here is a query, we are going to execute this one. So here we have already compiled our program and the program is ready and it is existing in the memory. So we are executing one code here. So this is a query and we want to execute the query here. So here you see it is producing, we are getting this answer, that is 1 2 3 0 4 5 6 7 8. That means it was in the first column of the middle row, the empty spot was there and it has reached to the goal node accordingly. Okay, so my DFS simplest is working fine, but the main difficulty in the DFS simplest is that it hasn't kept any trace that the target board position is already traversed or not. You see, if there is a cycle, if the target port position is already traversed by this algorithm earlier, by the other instances earlier, then it will form a looping. It cannot give us the ultimate result because each and every time it will reach to a target state of the board which has been traversed already. So as a result of that, if you go for a complicated board position like this, here this empty spot is at the bottom, then in that case, if I execute this query here, you can find that it is not giving us the answer because it will form an infinite loop, and you can find that this GNU Prolog has stopped working here. So it has stopped working. So if I close this one, so this window is getting closed. So that's why we are going for another version of this DFS simplest. So here it has been labeled as DFS. So here we are doing the same thing, but one thing we are doing, that means whatever the board positions, the least structure we have covered, we have traversed already in our board arrangements, we are keeping that one in a trace, in a respective list that is known as a checked. And if this target board position is not a member, so it denotes not, is not a member of this checked list, then we shall go for this DFS S2, and this S2 is also getting prepended to the checked list. So it will prohibit our board positions to come which has been traversed earlier. So now if I execute this query on this, so here also the program has been compiled and it is found okay. So I'm getting this answer perfectly okay. And here also if I just write here length of this path and I'm keeping this one in n, so it is giving me that how many transitions I had to make to reach to my goal node. So it is telling that only one transition we are requiring. So that's why this DFS is better than the DFS simplest, because it is keeping a trace of those board arrangements, those lists which we have got on our way to reach to the source board position to the target board position. So this is our algorithm. We have shown you that how my program is working and how to bring a betterment in our execution, in our coding. In this video, we are going to show you that how the family relationship can be expressed in Prolog language. So here we are having one family tree. So Pam is the parent of Bob, Tom is the parent of Bob, Tom is also having another child, that is Lige. So this is our family relationship tree. Prolog is a programming language for symbolic, non-numeric computation. It is especially well suited for solving problems that involve objects and relationships and between the objects and so on. So objects and relationships or relations between the objects will be depicted in our Prolog language. In Prolog we can write this family tree as like this one. So parent Pam Bob. So Pam is the parent of Bob. Parent Tom Bob. So Tom is the parent of Bob. Parent Tom Lige. So Tom is the parent of Liz, and so on. So there we are having, this is known as the facts, that means the known knowledge base. So also known as knowledge base, also known as facts. So in this way we have written this, and these can also be under the category clause, and each and every clause must be terminated by a full stop, and that is the syntax of this Prolog language. So our example program has helped to demonstrate some important points. So what are the points we have noted here? We have defined parent relation by stating the n tuples of objects based on the given info in the family tree. The user can easily query the Prolog system about the relations defined in the program. So whatever the knowledge base we are having, we can generate the respective queries and goals to get the answers. A Prolog program consists of clauses terminated by a full stop, as I mentioned earlier. The arguments of relations can, among other things, be concrete objects or constants such as Pat or Jim, or general objects such as X and Y. So here this X is written in capital and Y is also written in capital. So there the general objects can also be called as variables. Objects of the first kind in our program are called atoms. So here we are having this Pat and Jim, they will be known as the atoms, and objects of the second kind will be known as the variables. So here this capital X and capital Y will be known as the variables. So variables can be written in Prolog either starting with a capital letter or with one underscore. After that it may have small or capital letter combinations, it can have underscore, it can have digits and so on. Questions to the system consists of the one or more goals. So let us define the sex of our family members. These facts can be written in two different ways. You can write in this way or you can write in this way. So that will depend upon your decision that how to define the sex of the family members using facts written in two different types of clauses. You can select any one of them. So let us see how can we define mother and sister relationships. So how to define the mother relationship? X will be the mother of Y if X is parent of Y along with X is female. So how to write this one in Prolog clauses? We can write in this way. X will be the mother of Y. Here X and Y are written in capital letters. That means they are the variables. So X and Y, X will be the mother of Y if parent XY and female X. So if two clauses are satisfied at the same time, because here we are having this comma denotes AND logic. So on the other hand, semicolon denotes OR. So here these two conditions are connected by AND this is known as if. Colon dash is known as if, and each and every Prolog clause must be terminated by full stop. We know that clauses can be divided into two categories. One is the facts, another one is a rule. So this is our rule, and where we wrote something like your parent Tom Pat, so that was our fact, that is a knowledge base. So sister, how to define sister? So come to this diagram here. So X will be the sister of Y if X and Y, if they are having the same parent, let it be Z, also in the capital letters, variable, and X is female. For Y, I need not to mention the respective sex for Y. So how to write this one in Prolog clauses? So sister XY if parent ZX and parent ZY, that means Z is the common parent for X and Y both, and female X. Last one, and X is not equal to Y. So if X is not equal to Y, X is a female and X and Y both are having the same parent, let it be Z say, then you can say that X is a sister of Y. Similarly, you can define the father. You can easily see that here we had the female, here we have written male, and similarly we can also go for has child. So X will have the child if X is parent of someone. So someone, how to write someone in Prolog? That is underscore. Underscore means what? Means anonymous variable. So a variable can be underscored and it is having a special meaning that it is anonymous variable. So brother XY, so we have defined sister. Now brother XY, so parent XZ, parent ZX rather, and parent ZY. So that means the same parent for X and Y, and male X and X is not equal to Y. So in this way also you can define brother relation. So here we have defined our parent, our sex relation, then mother, sister, father, has child, brother, and so on. So let us go for the practical demonstration for the better understanding how these codes should be written and how to execute them through certain queries or goals. So here is the demonstration for you. This is a sample Prolog program. A Prolog program will have mainly three sections. One is the domains, next one is the predicates, and the last one is the clauses. So under domains, we will be having name is equal to symbol or some sort of declarations like this, where symbol indicates that it is of the type text or string, and name this is my keyword, my word I've given. We can use some other names here also, no issues. So predicates, under the predicates, we shall be declaring all the predicates under which the clauses will be defined. So here we are having this parent, so Pam and Bob. So we have written this one like this: parent name, comma name, female name, and so on. In under the clauses sections, we shall discuss or we shall define our databases. So this is our Pam, who is female, and Liz, Pat, and all of them are female. So here I am declaring some other knowledge base, and this is the respective knowledge base we have defined. Now, this is the clause, and this is the first clause we have written here is known as the mother. So mother x comma y. So you see, under clauses we are writing such, these are known as the rules. These are known as the rules, and these clauses will be known as the facts. Okay, so facts and rules will be the members of the respective clauses. So mother x comma y, this symbol indicates if, and this comma indicates and full stop or period will be indicating the terminating of the respective clauses. Okay, now, so mother x comma y, if parent x comma y, comma means and female x. In this way, we have defined father. Has child means x will have a child if parent x comma underscore. Here underscore indicates that it is anonymous variable. Sister x comma y, if parent z comma x, parent z comma y. That means if z is the common parent for x and y, and if female x, then and x is not equal to y, then we shall say that sister xy is working. In other versions of Prolog, instead of having this operator, we can also use the operator like this one in other versions of Prolog. But in case of GNU Prolog, we'll be going for this operator. So similarly, we have defined this brother, parent zx, parent zy, and male x, and male and x is not equal to y. So in this way, we have defined the respective facts. These are the facts, and these are the rules under the section clauses. But in case of GNU Prolog, these clauses, predicates, and domains, these sections are not required. So that's why we are putting them under block comment. So in case of Prolog, we can write comments in two different ways. In case of single line comment, it can be preceded by the percentage symbol. In case of block comment, it should be including the total block under slash star and star slash in this way. Okay, so we are having this female, male, parent, mother, father, has child, sister, and brother in this way. So now let us go for the respective execution. Here we have already done the change directory. So under this particular folder, that is Prolog workspace, under this particular folder Prolog workspace, we have saved this file, that is block2.pl. So now the program has been compiled, and it has found that no error is there, so it is executable now. So now let me execute with some respective goals. So I'm going for we know that in case of variables, the variable name must be starting with some capital letters. So now if I want to have any other options pending, then I can give semicolon there, and here we are getting two. One is Pat, another one is a Peter. Let me check. So Jim, so Pat, Jim, so it is Peter, Jim. So that's why you got two answers. Now let me go for mother. If I want to terminate the solution here, then I can press enter. I can hit enter. But if I want to get all other combinations, then I can press here semicolon. So these are the options. So two answers I'm going to get from our knowledge base. So these are the answers are there. In this way, I can get it. If I go on pressing this semicolon, then all the answers will be obtained. Okay, let us go for brother. So in this way, the program can be executed, the goal can be written. So these are known as the goals. So here, these are the respective answers I'm getting from this database. So this is a program we have written in Prolog, and here in other versions we may be having these domains, predicates and clauses, but in case of GNU Prolog, we may start our program writing keeping them under command block. That means they are not going to be executed. We are going to discuss a very important topic, that is the data objects in Prolog. So what are the different categories of data objects that are allowed in the Prolog? We shall discuss that one with some examples. So this is the respective tree structure to show you that what is the categories are there and which is the subcategories. So data objects mainly can be divided into two parts. One is your simple objects, another one is your structure. Structure means against one functor we shall have multiple arguments. So structures will have multiple arguments. Let us suppose there is a particular structure with a name date and it is having three values, say 20 June 2017. So that is a structure. We shall have a separate video on structure, you can also watch them. So simple objects can be categorized into two heads. So here these are the constants and these are the variables. So what is the variable? The variable is nothing but a symbol which can hold multiple values, but one value at a time obviously. So in this case of variables we can have say lowercase letters, we can have the capital letters, we can have the digits, we can have the underscore. So a variable name can start with some capital letters, a variable name can be starting with some underscore. So all these things we are discussing in that video where we were discussing only the variables. These constants can be divided into two categories, one is atoms and another one is the numbers. Say TOM, Tom, written in the lowercase letters can be treated as an atom, and these numbers can be either integer or real. But real numbers are not so much used in our Prolog codes. We maximum we go for the integer number representations. So examples, let us go for the examples. So atoms, Tom, Pat, X 100, X underscore 45 will be a good example of atoms. Numbers 100, 1235, 2000.45, this is a real number, these are the integer numbers. Variables, so it can start with the capital letters, it can have the lowercase letters also, can have also the digits, can also start with some underscore and then followed by some other characters. Structures, say day, so 9 June 2017, so that this is known as the structure name, also known as a functor. Point 10 comma 25, a point is a functor, 10 and 25 are two arguments. So these are the representations of structures. So we are having separate videos for all of them, for the better understanding and for more examples and discussions. Please watch all of them in the respective sequence. Thanks for watching this video.